If you're ready, we're going to do our second trip today. So we're going to go to the Saturnian system and look at satellites that are around Saturn, and in particular look at Titan and Enceladus, that are two of the satellites that, as I mentioned before, show indications of habitable conditions and becoming deep habitats. So we're going to go into the system of the Lord of the Rings. So everybody knows why Saturn is so famous. It's because it has the rings, and it has numerous children. And if I ask you how many satellites we have around Saturn, you'll say 60 something. Yes, that's true. It's 60 something again. It's funny, huh? But we're at 62 satellites. So we have numerous children, and of those of you who follow mythology know what Saturn did with his children? He ate them. Okay. So if some of you are asking yourselves the question why Saturn's satellites are not the names of his children, that you remember his children were the Olympian gods, including Jupiter and so on, it's because he ate them and nobody thought it was convenient, conventional enough to give the names of his children to the satellites. So we had to find different names. And Saturn is very important and very dear to my heart because I come from Observatoire de Paris, and this is Observatoire de Paris in the older times, in the 17th century, and here's one of the directors of the observatory, Cassini, observing Saturn. You can see up here in direct line with his little telescope, and writing down, scribbling. I've seen the rings, and I've seen 4 of the satellites, and taking notes. And so the Paris Observatory has a long history of observing Saturn, and of course this is a very old image before everything was surrounded by buildings and Avenue d'Enfer Rocheron and so on, but this is how it looked at that time. So again, Saturn, what we had before, was found and revealed essentially by the Voyager missions that arrived in the Saturnian system in 1980 and made several observations, including of the planet and of its satellites. But I'm going to be discussing essentially today a different mission. It's the Cassini-Huygens mission, and I just mentioned Cassini, who was a French-Italian astronomer. He discovered several of the satellites and, of course, many things about the rings, including the Cassini division, which is a gap between 2 main rings there. And the name for Huygens came from Christian Huygens, who is a Dutch amateur astronomer and who discovered several, again, of Saturn's rings and its largest moon, Titan. And this is a picture of the satellites around Saturn. Here you have the planet itself, its rings. Here you have the locations of some of these satellites. You can see that the satellites like Titan, Hyperion, Iapetus, and so on are located further out, and some of the other satellites like Enceladus and so on are in an inner space with respect to distance from Saturn. And you also notice that among the satellites we have around Saturn, there are differences. Most of them are these small icy bodies, but there is one big exception, and that's Titan, so we'll be talking more about Titan later on. But the Cassini mission is something that we have been working on, some of us, from before my PhD, so a very, very long time. It's something that started as a concept in the 80s and started development in the 90s. In the 90s, we sent proposals. We put together this mission that's a collaboration between the US and Europe, a very strong and fruitful collaboration that built this spacecraft that you see here with all the instruments on board, a very powerful orbiter with 12 instruments, and then it carried the Huygens Titan probe. That's the achievement of the European Space Agency that was put together with 6 instruments on board. But for some of us who worked on this mission for quite some time, we we thought of it as our product, as a human being. It has its human functions. First and most of all, it's cell phone, because no human these days goes out without a cell phone. It has a brain here, that's the computer. It has eyes, those are the cameras. You can see it here in the configuration. And of course, it has the baby. The baby was the Huygens probe that we sent into Titan's atmosphere, and it was carried. You can see it back here, and we'll say more about it later on. It was a mission that took quite some time to develop. A lot of us devoted quite some time to it, and it's still going on strong today, as you'll see in a minute. And it had a very, very long journey. It started from the Earth, and the Earth, of course, today is Litesh. We're all here. And it went to Titan, all the way out here. The journey, if you had gone straight, it would be 1,200,000,000 kilometers, but the distance the mission traveled in 7 years was actually 3 billion kilometers, because of course you need gravity assist to make several flybys and gain the energy and the kinetic energy you need to go all the way to Saturn. We're talking 10 astronomical units, so it's really very far away. And this is a fantastic mission that was launched on 15 October 1997. Have you all seen launches here? You've attended launches? All of you, right. Oh, okay. How would you like to see a launch? Okay. All right. So we're at Cape Canaveral, 15 October 1997, 4:43 in the morning. We're watching from here. There's us, the river with the alligators,
T-minus 15.
and the stand.
T-minus 10. 9, 8, 7, 6, 5, 4, 3, 2, 1, and liftoff of the Cassini spacecraft on a billion-mile trek to Saturn. Pitch program is in, roll program is in.
We had a beautiful night.
We have cleared the tower, and the Cassini spacecraft is on its way to Saturn.
We even ordered
Plus 20 seconds.
the clouds.
So go. Jupiter Inlet Tracking Station now acquiring data. All systems go. Everything is go at this time. All systems are go.
All right, all systems are go, and the next step, of course, is the separation from the rockets that
Vehicle going through maximum dynamic pressure, max Q.
give Cassini then the autonomy
Continuing to be go.
to proceed on its own, on its trip. So, beautiful launch, right? I mean, it's the most beautiful I've ever seen. Oh, I've only seen one, but that was the best. And then you go on a trajectory, you can see here, with multiple flybys, and then you go out to Saturn, and of course you fly by also by Jupiter. So here's what happened. In case you missed it, there was a launch. We flew by Venus, we flew by the Earth in 1999, and we made some measurements, and in particular we looked for intelligent life. We found life. We found evidence for life. The intelligence, we had to come back again. As Carl Sagan said, it's not mine. But anyway, so in 2000, early 2000, we flew by asteroid Mazursky. Late 2000, we went by Jupiter. And which is the other mission which was still around Jupiter in 2000? Galileo. Somebody listened to my earlier talk. And so here you are in the Jupiter system. You're flying by with Cassini, and you have the Galileo mission there. And some people are thinking, maybe we should turn on the instruments and make measurements. But remember, we're going to Saturn, right? Turning on instruments is a tricky thing, because you never know if you can turn them back out again and restart. And somebody sitting over there, Laurence, knows about the difficulty of getting back to the same configuration again once you've lost it. So we're there in the Jupiter system, and some people want to make measurements and turn on the instruments, some people don't. So how many among you here today would turn on the instruments and make measurements? Only one temporary person, only one would like to do that. The scientific reason is that having two missions at the same time give you measurements that you cannot do with one mission alone. In particular, I'm told by my friends who work on plasmas, magnetospheres, for the magnetospheric parameters in the system. But he was right. All of us who said, no, don't touch the instruments. We're going to Saturn. Who cares about Jupiter? Lost the game. And we turned the instruments on, and we made quite a few measurements in the Jupiter system, including measurements of Jupiter's atmosphere, actually, with different components from stereoscopic, different areas and so on. And they were quite useful. But thank God we managed to shut everything down again and get all the way to Saturn. You see here one of the first pictures in October 2002. And here's again how we got into orbit around Saturn, and you can see the different trajectories. The wonderful thing about this mission is that it doesn't stay in the ecliptic plane. It goes up and down elliptic orbits and different things, because we're working throughout the whole Saturnian system. And this mission was supposed to end in June 2008. And I'm sure you all know that it's still going on strong today in 2017, so it's almost 10 years more than what we had foreseen before. 10 years, total 13 years of a wonderful mission that had to face a lot of different things and a lot of different challenges, among other crossing the rings. When we got into orbit around Saturn, we had to dive through the rings and come up again in order to leave the ecliptic plane and make all the different trajectories I just showed you. And of course, crossing the rings is never easy, because if some of these particles happen to hit one of the instruments that we have on board, they could kill it. All right, they could cause damage. And so we were all sitting in Darmstadt, very, very in the control center of ESA, and being very worried about what would happen. But especially the engineers, who were saying, no, let's not cross the rings. Why do you need to make this time? So anyway, we won again. And then so we crossed the rings and we got into orbit. And one of the amazing things, and we've seen many amazing things since then, but one of them is, I don't know if you heard about the famous hexagon, this storm that rages in the northern pole of Saturn, and we've seen this and followed it, and it's something that was very complicated to reproduce. It's a storm that is, I think, 10,000 times stronger than what you have on Earth, for instance, and rages there and then goes to the South Pole. Very, very interesting phenomenon. This hexagon here, some people in the UK have managed to reproduce in a lab, but it's not easy to do. So among Saturn satellites, several of them are very, very intriguing, but one of them attracted attention early on, and that's Enceladus here. Enceladus and the tiger stripes is something that people have been working on for quite some time, but as I said before, nobody knew at the time that this moon was going to prove to be so interesting. The thing we knew, even from images that we had previously from the Voyager missions, were those tiger stripes, as if a tiger clawed through the surface of this satellite. And these are these canyons here that you see bluish. It's at the South Polar region. What we didn't know was that actually from the South Pole of Enceladus, there emerged these kind of plumes, the geysers, that we only first detected due to the fact that they caused a distortion of the magnetic field lines. So the magnetometer detected this atmosphere here because of this distortion in the magnetic field lines, and they said, oh, go take a closer look to the camera, and the camera said, nah, there's nothing there. And then they went there, and they saw this. And the interesting thing is that the composition of the plumes, these geysers here, is water vapor essentially. So how do you get water vapor expelled there? You really need to have liquid water somewhere, warmed up at least, somewhere underneath the surface, but not very far down underneath the surface, because otherwise you cannot create geysers. Water vapor, but look at the other stuff here. So I've got my water, but I also have organic chemistry here. I've got all these components here, carbon monoxide, methane, carbon dioxide, simple organics and complex organics that we found flying by with the Cassini. So, of course, the water vapor ejecta has strong implications for the habitability zone. I explained before why now this habitability zone has moved outer in the solar system. And we have the indications for the presence of organic chemistry. And one of the attractive things here is that, of course, we used the spacecraft to fly through the plumes 25 kilometers only away from the surface. We just flew through. And of course, the engineers were going crazy. How are we going to recover our spacecraft? But it's a tiny moon. It doesn't have such a strong gravity. No. Yes. And so we flew through here. Dramatic plumes 400 kilometers out into space and many locations, and they come out from the tiger stripes. We made measurements of some of the instruments using a spectrometer, for instance, that gives you the temperature, and we found that these canyons are warmer than elsewhere. The temperature there shows 170 K in the Damascus sulcus that you see here, for instance. So it's warmer regions, and there have been models, of course, that say that, for instance, you have tidal heating here in the interior of the satellite, then you get hydrothermal circulation, convecting ice, and then you create the conditions with a pressurized liquid water pocket at 270 K even to vent to the surface, create this, go through these cracks that exist there where the ice is shallower, and then eject these plumes of water vapor out in the space. And so Enceladus is really a place where you have several of the conditions for habitability, as my friend Chris McKay was saying. Instead of going drilling or scooping or melting or digging, you can just fly through and get a collection of everything you have in there. And this is actually how we got an indication of what's the composition of the plumes. And it's basically icy moon material delivered to your door. So if we do anything again in the Saturnian system and we want to study Enceladus, it's easy. We don't have to land. We don't have to do anything. Same for Europa that we were discussing before. If you have plumes, you can get some of the material that is injected and then make measurements and get an indication of what you have inside in the interior. So very exciting and very interesting moon Enceladus, but la vedette, so in the system is, of course, Titan. Has been Titan for quite some time. I can't resist showing you this very nice image again from Cassini. You see the rings and this Titan behind and a small moon here. And most of the images you'll see, unless I say otherwise, are real images. And sometimes you could wonder, but all of them are real images. The spatial resolution that Cassini achieved with the cameras and all the other instruments is amazing. There is nothing that can replace an in situ investigation of a planetary object or an exoplanet when we get there. But you do need in situ investigation. And Titan has been extremely exciting a long time ago. I said Cassini-Huygens discovered it in 1655. We've had some first measurements indicating atmospheric limb darkening. That's a way of saying that it had an atmosphere, and we knew it since the early 20th century. Then we detected methane in there. Everybody got very excited. The Voyager missions gave us quite a few measurements. For instance, the distance from Saturn is 20 Saturn radii, quite a distance away, which is, we think, why Titan was able to keep its atmosphere. If it was sitting very close to its planet, Saturn ate, remember, his kids, so he wouldn't have had any qualms about removing the material that formed Titan's atmosphere. There is a theory also that this is a secondary atmosphere. How the N2 got there is still in debate, but we think that if it kept this envelope, it's because it's sitting far away from its planet. We have also several other indications. One of them I find very important is the gravity. Wouldn't you all like to feel 7 times lighter today? Somewhere? I would. I know. So the gravity is 1/7 of the Earth, so you're fine there. You've got conditions very similar to our own planet. The gravity is perfect. We made a lot of observations from the ground before Cassini arrived there. And I just want to walk you through some of these elements that we found. One of them is that, as I said before, Titan is very big. It lost to Ganymede by 100 kilometers only. But for quite some time, people thought Titan was the largest satellite in our own solar system. You know why? Yes, because the atmosphere around it, as seen from the Earth, made it look larger. That subtended a larger diameter in the sky than Ganymede did. But the ground itself is 100 kilometers less than Ganymede. It's larger, of course, than some of the planets, including Mercury and all the other satellites. And the other interesting thing is that Titan follows Saturn on its rotation around the Sun. Saturn is tilted. You can see here that this tilt is very similar to the orbital inclination we have for the Earth. And this, of course, means that we have on Titan seasons. Except that Saturn takes 30 years to go around the Sun. So how long is a season on Titan? You really need a machine to do 30 divided by 4? Okay, all right, 7.5. So 7.5 years of winter, 7.5 years of summer, 7.5 years of autumn, and so on, and spring, and so on. So you have to start thinking, when you think about Titan, in different terms as far as time periods are concerned, right? And it's important to think this way, because everything I'll be saying, when you think, oh, that's like the Earth, think it's, 7 years respect to 3 months longer. But that's not the only interesting thing. How many of you keep Muriel, mumbling, 24 hours a day is not enough.
I agree.
You agree, right? Oh, no, I need more time. No. Okay, so Titan.
Wonderful.
8 days day, 8 days night. You can sleep for 8 days. Each day. And then you can work for 8 days, okay? Yes, you can't have it all. But anyway, so this is a completely different timeline. Think outside the box. This is a body that is sitting out there with different time properties, but as I'll show you, has very many similarities still with the Earth. I think it's worth for you to give it some consideration, okay, for your future plans. Holidays, for instance, things like that. It has a very dense atmosphere. It's seen here by the Voyager missions, actually. This is a detached layer. This is the atmosphere. Very large envelope of haze surrounding the moon. The haze is composed of hydrocarbons, essentially. That's what makes the haze. But the atmosphere itself has a very common constituent with what we have on Earth. What are you breathing right now?
Nitrogen.
So who said oxygen? Nobody said oxygen? I think I heard yes. And somebody said nitrogen. So 80% of what you're breathing right now is nitrogen. And we tend to forget it. To be exact, 78%. Oxygen is 21%. But you heard, of course, before that we need the oxygen. So everybody thinks oxygen, but you're not breathing oxygen. You're breathing 80% of nitrogen. On Titan, you have 95% of nitrogen in the atmosphere. And then you don't have very much oxygen. That is a small problem for some of us, the way we have developed. But if we had developed differently, for instance, these other ecosystems in the water that don't like oxygen, we might have enjoyed ourselves on Titan with methane and other hydrocarbons, hydrogen. All of this creates nitriles. Nitriles, some of them like HCN, hydrogen cyanide, for instance, are called prebiotic molecules, I'm told by biologists, and they're sitting at the basis of the macromolecules that lead to life. And all of this, I'm just citing what I know because I'm not a biologist. But on Titan, you have this atmosphere, very dense atmosphere, extending at 1,600 kilometers out there, in which you have all this organic chemistry being created. It diffuses down into the atmosphere. It creates even clouds. But instead of water and water vapor, you have methane. So when you think Titan, instead of water and water vapor, you think methane and hydrocarbons. It's not easy, but you get used to it. Anything liquid on the surface is hydrocarbon. The pressure on the surface is 1.5 bar, almost the same as we have on the Earth. The little thing you're missing is the temperature. Minus 180 degrees Celsius. And I know you can find some pretty cold places on Earth, but I don't think you can find minus 180. Okay, so little problem there with the temperature, but some people like to go skiing. Okay, so you go on Titan, you have 7.5 years to go skiing. The other thing, very similar to our own planet, temperature inversion and greenhouse effect. Greenhouse on Titan is caused by the haze and the hydrocarbons you have in the atmosphere. It's not the water vapor. But that's not a problem. You have greenhouse gases like methane and so on. And this increases the temperature down here to a balmy minus 180 degrees Celsius, as I said. And so from everything you've heard these days, you know that Titan and the Earth have quite a few similarities. You can see here the atmosphere, which may be something similar to what we had on the primitive Earth. I know some of these theories about methane and ammonia have gone down the drain in the recent years. But some of the things that we have on our own planet, like volcanism, volcanic sources, some of the ways we have for creating polymers, some of the ways we have, as you heard, to have inorganic molecules and organic molecules at the same time present in an environment are quite similar to what we have on Titan. And this is why we've always defended the idea that Titan provides a good analog as a natural laboratory, planetary scale, to study some of the some of the conditions that prevailed in the primordial atmosphere of the Earth. And so we send a mission there, but there's still quite a few queries as to how this methane cycle on Titan that starts from evaporation from a liquid surface, probably having photolysis in the atmosphere, producing heavier molecules, condensate and dropping again on the surface, similar to the water vapor cycle on the Earth. Where do we get the methane? Because the methane should have disappeared in 35 million years and needs to be explained. We need a reservoir that we're still looking for, and we don't know exactly what the internal structure is, and this is why we sent the Cassini mission. And the Cassini mission provided several elements to this mystery. One of them was to show that the organic chemistry was even much more complex than we thought. We had only studied the organic chemistry in the stratospheric layers of Titan, that is the layers between roughly 50 and 500 kilometers in altitude. The stratosphere on the Earth extends smaller altitude levels because Titan's atmosphere is much, much more extended and denser. But we had only indications via spectroscopy of what's going on in the stratosphere of Titan. We knew, for instance, that you started out with the methane here, the molecular nitrogen here, and that you produced all these different molecules, including what I mentioned, the prebiotic, the nitriles, on the one hand, the hydrocarbons on the other hand. So I have some of my schnapps there, I have some of my nutrients. And then I end up having lots of haze in the atmosphere. But we didn't know that this chemistry actually started very high up in the atmosphere, above 1,000 kilometers, with the production via energetic particles and sunlight of products from the molecular nitrogen and the methane via ionization, dissociation, heavy ions, creating more and more complex molecules, including benzene. We were all looking for water, talking about water. I have a chance here to show you that there's water vapor in the atmosphere of one of these moons. Titan is the only other moon in the solar system to have a significant atmosphere. Okay, we're talking about tenuous atmospheres around some of these moons. This is a real atmosphere. This is an atmosphere denser and thicker than the Earth's. And it's made of nitrogen, essentially. But it also has a little bit of water, and we needed the water to explain the presence of CO2 and CO in Titan's atmosphere. We found the water thanks to the Infrared Space Observatory, ISO. Here are some of the detections I made with the ISO observatory. The water vapor at some 10 to the minus 8 per weight in the atmosphere, and this is the detection of benzene in Titan's atmosphere, for again 10 to the minus 10 to 10 to the minus 8 mole fractions. So Titan has a very complex atmosphere, and if you don't believe me, just look at that. This is a table we put together with all the gaseous components we find in Titan's atmosphere, including isotopic ratios and including what we have now in the upper part of the atmosphere that doesn't necessarily diffuse lower. So Titan has a very complex organic chemistry in its atmosphere. Very interesting world. So I got my nutrients. How about evolution of this atmosphere? And we have, I said, seasons on Titan, and this atmosphere evolves, but within the mission that we've had on with Cassini, we have only studied 2 of these seasons, right? So we haven't seen a full rotation yet. So we're just now beginning to witness the winter in the South Polar region, and we see very, very significant changes in the atmosphere in the Southern Polar region of Titan, enhancement of many molecules. Similar as on Earth, there are changes in the atmosphere due to the seasonal effects. Okay, very interesting atmosphere. Now let's look at the surface and the interior, of course, because we're interested to see what's underneath the surface. And these are some images taken by the visual infrared mass spectrometer around looking at Titan, and you see all these different areas, and you can see that the equator of Titan is essentially dark, poles are essentially bright. We're still missing some patches there. So we saw different things on Titan. Some of them were taken by the Cassini radar with a very high contrasted capability, and you can see here some of these regions where we have white terrain and dark terrain. And of course, you can all see what's on the upper left image. What do you see on the upper left image? I'm giving you all the hints. What do you see here? Crater. And what's this? Crater. You see even the little dome in the middle. We have very, very few craters on Titan. The reason is twofold. One, the surface is younger, has been experiencing resurfacing. Second, erosion, aeolian processes due to the atmosphere change the surface. Very few craters, but here is one of them. I'm sure you've all seen it. And the other thing, amazing thing, dunes. This is the Earth. Longitudinal dunes created by wind. This is Titan. Longitudinal dunes created by very little wind. Not much wind on Titan, but they can still bring these particles together in these formations because the particles are not sand. These particles on Titan is ice. Very small icy particles with a little bit of organics inside, so much less heavier than on Earth. So you can still form the longitudinal dunes. But of course, the essential thing was the discovery of lakes on Titan. And lakes on Titan, this dark bluish patches you see here. At this time of the year, I remember a year on Titan is 30 years, this time of the year, the lakes are in the northern pole. They're all concentrated there. There are a couple of lakes somewhere here near the equator, but essentially in the northern polar region. And we think this is a seasonal effect, but maybe not. Can they compose the missing CH4 reservoir? We don't think so. All the hydrocarbons that you have in the lakes today, and all we can see from bathymetry, is indicating that there's not enough hydrocarbon on Titan's surface today to account for the presence of methane remaining in the atmosphere. So we need a subsurface reservoir also for methane. But we have these wetlands, and it's really fun to have the wetlands. You can see them in the North Polar region. This is radar images, and we're flying over Titan's northern polar region. You can see these dark spots appearing all of a sudden, and it's the lakes, and you can see the different forms they have, and you can see that some of them actually connect, and this is the radar measurements coming on top of the schematic. And these regions look at the shorelines. How do we know it's lakes? It's because look at the fractal shorelines. This is what geologists, I think, say that you have to have if you have lakes. And look at the resolution we have and the little islands in the middle and of the lakes and the shorelines, and how different the terrain is between the exposed regions and the lakes. And because they're so dark, we think it's necessarily filled with hydrocarbon liquid. And you can also see that we have many little lakes or and rivers along Titan's northern polar region. How do you create those things? Is that you look at weather. Climate is what you expect, weather is what you get, as Mark Twain said. And the clouds on Titan, we followed the clouds on Titan for quite some time. And here we are again above the lakes in the northern polar region. And you have the clouds. We have found clouds in Titan's northern polar region, and we see them evolving. But we also see them evolving actually around the equator in some cases. And this is what we think fill the lakes. So let's go take a closer look at some of the lakes on Titan.
Titan is the only planetary body besides Earth that we know has lakes. At 290 degrees Fahrenheit below zero, the only liquid that makes sense there is a combination of methane and ethane. This lake is Ontario-Lacus in Titan's southern hemisphere. It's a little smaller than Lake Michigan. We've colored the lake black because we think that's probably its real color, although we don't really know for sure. We've exaggerated the heights of the shoreline features to make them easier to see. Notice these hills, probably made of water ice. See how the liquid has flooded up the valleys? Further north is a long, smoother beach that looks like it's been shaped by waves. You can see some lines along the beach that might be old shorelines, like bathtub rings, so we know the level of the lake has changed. Now we're turning east to a very obvious bay that cuts into the beach, so it's likely to be younger. We'll cross over the lake, you'll see some flooded valleys, and in the background is a large river that makes a delta, like the Mississippi River. Its shape means the lake is shallow and the river is slow. Ontario's shore is surprisingly like earthly lake shores. Pretty amazing to find something this Earth-like 800 million miles away.
Right, and it's indeed amazing to see that with completely different materials, you can still get very similar features, right? Behaving in a similar way to what we have on Earth. But it's not only the lakes, you know, it's also some of the other features that we find there. And for instance, canyons.
We've been flying around Saturn and passing by Titan periodically. We've been able to map out the surface brightness as the radar sees it. We see geologic
The radar
processes
that we've been
are
flying
very
around
similar to
Saturn
what
and
we see on
passing
the
by
Earth.
Titan periodically,
This
we've
is
been
a
able to map out the
computer-generated
surface
3D
brightness
fly-through
as the
of
radar
area
sees it.
of
We
karst
see
topography
geologic
on Titan.
processes that
It was
are very
generated
similar to what we
by
see on the Earth.
inferring the topography and
This
then
is a
laying radar
computer-generated
image down on top of
3D
the
fly-through
3D
of
map.
an area of karst
This
topography
area
on
is
Titan.
an area
It was
called
generated
Labyrinth
by
on
inferring the
Titan.
topography
It's an area
and
of
then
karst
laying a radar
topography
image
very
down on
similar
top
to
of the
karst
3D map.
topography we find on Earth.
This
especially
area
in
is
places
an area
like
called
Jamaica,
Sikkun Labyrinth
Puerto Rico,
on
or China.
Titan. It's an area of karst topography,
It's an area
very similar
where
to
liquid
the
methane
karst topography
here on
we find on
Titan
Earth,
is
especially
dissolved
in
in the
places
rocks
like
and
Jamaica,
produced a residual
Puerto
landscape
Rico,
of
or
just
China.
hills and valleys with no river valleys.
It's an area where liquid methane
So,
here on
yet
Titan
again,
has
another,
dissolved the rocks
process
and
that we
produced
see
a
on the Earth
residual
that we find on
landscape of
Titan,
just hills
making
and
Titan
valleys with no
very
river
similar to the
valleys
Earth in many
flowing
ways.
through the area. So,
Many similar
it's
to the
yet
Earth
again
by the
another,
features and the
process that we
processes,
see on
because
the
really
Earth that
what we
find
see
on
there
Titan,
sometimes is
making
built
Titan
or
very
is
similar to
created
the
by
Earth in many
processes
ways.
that we need to have, for instance, energy sources. And some of these things are, for instance, cryovolcanism, about which I'll talk in a minute. But just before to mention that the Huygens probe is what actually brought us the ground truth. The Huygens probe was launched into Titan's atmosphere with the 6 instruments you see here, performed a beautiful descent through the atmosphere using 3 parachutes to decrease the speed as we landed on the ground. And we were sworn that by the engineers that there is no way this thing is going to land. It's going to crash or it's going to sink. We don't know what we have on the surface, but you're going to get 4 or 5 minutes maximum tops on the surface. So we don't need the orbiter around to relay the data, right? Okay, 2.5 hours of descent, 3 hours and a quarter sitting on the surface on this very nice smooth beach, taking images of the same place, 360 images of exactly the same thing in front of us, because the engineers didn't have faith that this would survive. There was no, the Huygens probe was not a lander. It is a descent probe. Therefore, it had no instruments to perform surface measurements. You have to understand this. All right. The only instrument it had was a surface science package that had a penetrometer that was going to make measurements of the surface, and John Zarnecki, God help him, said it looked like a creme brulee. Now, everybody knows that English have no clue about what creme brulee is, and not to mention the rest of the French cuisine. But he got it all wrong. He thought there was a crust, the hard crust, and then you go through and you have creme. No. You had a very short, sandy surface, and this is where we landed, and we took images. One of the instruments had a small problem. That was the Doppler instrument that was going to measure the wind, but the radio signal of the equivalent of a cell phone in Saturn was picked up by radio telescopes on the Earth, 9 astronomical units away. And they allowed us to retrieve all the measurements we needed, including the atmospheric structure in Titan's atmosphere, where you see these gravitational waves in the upper part of the atmosphere, the stratosphere, the troposphere, and we measured very precisely the temperature and the pressure on the surface. We got tons of different measurements, but of course what interests the public is the DISR, the Descent Imaging Spectrometer aboard Huygens. That was the camera that also was making spectroscopic measurements in 3 different directions, so we had stereoscopic images. And this is the instrument itself. And remember, you're sitting at 10 astronomical units away from the sun. So already you're getting 1/100th of the light that you would get on Earth, arriving at the top of the atmosphere. We've measured that as you get to the surface, you get 10% of that. So 1,000th of the light gets to the surface. So it's very, very, very dark. And you want to take images. So what do? Here's the flash. And the flashlight came from one of my colleagues' idea, Emmanuel Lelouch-Meudon, who are sitting there with all these engineers and the important Americans, and they're saying it's going to be very dark. What are we going to do? We're going to stop as we go down. He says, "Oh, put a flash," and everybody laughed. And then the Americans went back, and they bought 30,000 little bulbs that you put in there to test if it would survive the trip. All of them survive. I mean, come on, sometimes you go back home, you click the light and it goes, okay, your bulb. But most of them survive. But still then they went and hired Thomson to make a special bulb that cost them several millions just to put on this flashlight here that we use anyway to go down to the surface. And during the descent, this is what you saw from the probe. This, by the way, the white is the track of the probe, and this is one of the images taken, a mosaic taken between 20 and 48 kilometers of altitude as you go down. Look at this amazing, amazing topography here, and you have several things that you can see, including channels here, a very dark area here in the middle before we landed that we think is a dried up lake, and several other things. I just wanted to show how this descent took place. It works. So this is the last parachute, Huygens going down to the, and you see the little flashlight, choop, and then you crash on the surface. When you find yourself on the surface, we bounced a little bit around, and this is how we broke some of the rocks around here, actually. And then the parachute fell far away, thankfully, from the probe, because otherwise we wouldn't have been able to make measurements. Here again, looking upwards from the surface, you can see it landing, bounced a little bit on this surroundings that is actually very similar to a riverbed of methane again, with these little pebbles all around it. And we went on for 3¼ hours taking images of what was around. So this is a very, very successful mission. I just wish the engineers would have thought to give us the relay from the orbiter to transmit more data and to make measurements on the ground. What you see here is evaporation of methane. We think evaporation of methane took place because, of course, the probe is hot. And so when it hit the surface that was wet, it created evaporation of methane that we were actually able to measure afterwards with different other instruments, including a mass spectrometer. So what we have on the surface after the landing is, this is from up in the atmosphere where we saw the channels that we have on Titan's surface, and this rugged terrain around here with hills going up to 200 kilometers. And on the surface, this is what we took. This is an assembly of the 360 pictures we took with all the pebbles. You can see the sizes. This is one of the rocks we thought we broke here as we bounced. And this is the colored image. It's not a false color. It's a color that we put together from the spectroscopic measurements. Because remember, this is a camera that also takes spectra, and the spectrum gives you the color. And this is the postcard we send to our friends. Postcard from Titan. You're sitting here. This is the probe, and this is what you see in front of you. Thankfully, we had the spectroscopic measurements and also the 3 directions of the camera. We could put together this 3D image of what you had in front of you. But also, we also got information, as I said, on the surface composition. Here is the surface composition. The methane evaporated from the surface. This is the jump you see here. All of a sudden, the methane quantities were up. This is an increase in the signal, and this is all the components we found on the surface: ethane, acetylene, cyanogen, benzene, carbon dioxide. So Titan's surface is really, really covered with a lot of organics. The composition is very important. All of these organic compounds are very important because there is strong indication that on Titan we also have a subsurface liquid water ocean. The spin measurements we made, this is a paper by Yes et al. In 2012, indicates the presence of an internal liquid water ocean. To explain them, Huygens also made measurements of electrical conductivity in the atmosphere, and also the results show in this case that the only way is to have a subsurface layer of Titan, which would be a subsurface ocean, to explain these electrical conductivity measurements. So all in all, we think we have a hydrosphere in Titan's interior. It's shown here in this internal structure by Toby et al. And because this radio wave at extremely low frequency was measured by Huygens, so we have a combination of measurements from the orbiter and the probe, we think we have this subsurface liquid water ocean on Titan. You can see these measurements here. And we also have active zones on the surface. I'm getting into energy sources now. Cryovolcanism has been defended on Titan for quite some time now, has been expected to exist. So cryovolcanism is something that has come up initially by looking at some regions on the surface where we see changes, variability of the surface brightness. As you can see here, Haute region is a region around Titan's equator. And here we have some indication of variations, these regions becoming brighter or darker. But I'll let you listen to Rosalie Lopez, one of the co-investigators.
Facula on Titan is the best case yet of a cryovolcano in the outer solar system. In fact, it appears to be two cryovolcanoes separated by a low area where we see some sand dunes. Here we see data from radar and the visible and infrared mapping spectrometer. This is false color to distinguish the different compositions of the surface. So the green areas are what we think are the volcanic areas, while the blues would be fields of sand dunes. Now we change the color scheme. The reds and yellows are highs, the blues are lows. When we got the topography, we see this tall mountain is about 1,000 meters tall. When you have a tall mountain and a deep crater and a low bait flow-like feature coming out of it, then it's very likely to be a cryovolcano. On Earth, volcanoes are formed by molten rock or magma that when it comes out is called lava. On Titan and other icy bodies, such as Saturn's moon Enceladus, we have cryovolcanism, that is very cold volcanism. And the material inside these bodies, the quotes magma, is not molten rock, is actually a watery mixture. Is water with probably ammonia and maybe methanol and other things. Material is being brought from the interior of the moon or the planet to the surface. This is important for a number of reasons, and one of them is that if you still have heat and enough heat to actually cause cryovolcanism to occur, and if you have water, then those are two of the ingredients that you need for life.
Right, so as you heard, we have heat sources also on Titan. This is very important. As for the case of Enceladus, it's one of the prerequisites for habitable conditions. So all in all, for Titan, we have the atmosphere with the nutrients, as I mentioned before, but other very interesting also aspects, the greenhouse effect, climate similarities, the seasonal effects. All of this is very, very important to study. Many geological similarities. The differences are ice on Titan is essentially rock on Earth. Remember, the dunes were not made of sand, they're made of ice particles. The methane cycle is a water cycle on Earth instead of the methane on Titan. And so we still need to understand the different actors. The organic chemistry is very, very important. It has very many similarities with the earlier prebiotic chemistry according to some theories. But as an object itself, Titan is very important because it could be actually the future of our own planet, because the conditions that prevail today on Titan, when the Earth becomes really heated up by the sun and the tropospheric temperatures around that suffers the equator blaze, we may have all the liquid transported actually at the poles, the North Pole or the South Pole of the Earth, and this is where you'd find the liquid. Whereas at the equator, you would have this rain pores, this scoring the surface and creating these organic deposits that we see also on Titan. Remember the dry lake where we dropped with a probe on Titan? It actually means that at some point it has rained. The riverbed I showed you with the pebbles are round. So there must have been some flow of some type of liquid at some time there. We don't see it now, but maybe at a different season, we see these rainfalls, very strong rainfalls at Titan's, near Titan's equator where we landed with the Huygens probe. And this could be something that our own Earth ends up doing also, having only dunes around the equator and all the liquid being assembled near the probes. So what next? Okay, so next is that the Cassini-Huygens mission is actually going to be there for a little bit of time, but only until 2017. The 15th of September this year, we're going to have to say goodbye to this mission. It's been on for 13 years. It still has some fuel. It produces beautiful images, but it costs some money. And if you want to make new missions, you have to sort of sadly get rid of all missions. So they're going to stop the mission 15 September 2017. Remember this date, it's going to be a sad day for us. But before that, a number of things are actually going to happen. This one is the best.
Cassini is there in the Saturn system now, has been making discoveries for the last several years, and there's more to come. By studying the satellites in the Saturnian system, we begin to understand something also about the origin of the solar system.
There is strong evidence now that most of the surface of Titan is in fact covered with organic material of some kind.
We're going to be looking at lakes on the surface of this moon in detail. We're going to be looking at the atmosphere to see how the climate changes over time.
We have some global circulation models that tell us as the winds pick up, we think there could be waves on the lakes of liquid methane.
Can you imagine anybody thinking that we would discover active cryovolcanism on one of these moons? Geysers? One of the things that we'll do in the next couple of years is make the first ever flyby through the plume when the plume output is at its maximum.
And then of course there's the planet Saturn itself. As we go through our series of orbits and as the seasons change, it's like having a brand new mission.
One Saturn year is nearly 30 Earth years. To be there for nearly half of a Saturn year is a once-in-a-lifetime opportunity.
The sun now is coming up on the North Pole, so we're getting to see territory that was in darkness when we first arrived in 2004. Pretty soon we'll have the whole hexagon and the hurricane inside of it illuminated by the sun. And then, of course, the mission's end itself is completely unique.
Starting in 2016, ending in 2017, these orbits will take us up and over the north and south poles of the planet.
We're actually going to dive in between the innermost edge of the D-ring and the upper atmosphere of the planet itself.
From that, we're going to learn how is Saturn constructed from inside out.
We'll also get the magnetic field of the planet, the mass of the rings for the very first time, and get to sample a place that no spacecraft has ever flown before.
This is a mission that cannot be duplicated. So we really want to take advantage of this opportunity to observe seasonal variation in the system.
Summer is coming in the northern hemisphere. So that's what's coming up next. Thank you. And then what? All right, so then what? So this is the ESA's fleet in the solar system. You have the different missions here. Some of them are close to the sun. Solar Orbiter is coming up. Bepi Colombo for Mercury is coming up. So we'll have had these places studied. In the outer solar system, after Cassini-Huygens, we have JUICE. And the way this works is, of course, that we have different categories of space missions, as somebody was asking, satisfying the cosmic vision plan with these themes that are organized around major questions we have for how the solar system and the universe in its whole operates. We have the medium class sized missions. The budget is 450 million euros. They have to be ready to go, so no technological challenges here. They come around every 2 or 3 years for the launch period of time. Next one is M1. M1 is the Solar Orbiter. It's supposed to fly in 2017. It's been delayed to 2018 now. After that is going to be M2, that's Euclid, and after that is going to be M3, that's Plato, 2022. We've had the M4 call and we have had the M5 call. Large class missions, budget 650 million euros, some possibility for making some technological developments. You can see here that we need also international collaboration. These are the dates of what we've had so far. The latest call was for the M5 for launch in 2029. There's going to be 2 large missions, L2 and L3. You may have heard L2 is an X-ray observatory called Athena Plus. I insist on the plus. I'm Athena. That's Athena plus. Even plus plus, I think, now they call it. Anyway, and then the L3 is going to be the gravitational wave observatory that is now being constructed. And so here is actually what ESA has in schedule right now. So I'm showing you the most recent view graphs. The large missions, L1 JUICE, the X-ray, the Athena Plus Observatory, and the Gravitational Observatory for the third large mission, and the medium-sized missions, M1, M2, M3, M4. We have 3 candidates, Ariel, Tor, and XIPE, being studied at the moment to see which one the selection should be this year. The M5 call has taken place, lots of proposals received, and then there's going to be an M6 and M7. At the same time, there's contributions from the European Space Agency to the JWST, a very important instrument if you're looking also for planets characteristics. And there are junior partnerships for different kind of missions, the Spica with Japan and the Europa Clipper that I mentioned before. So all of this is coming up, but as far as Titan is concerned, there are some future concepts. You can see, helicopters. We're even thinking of sending somebody there. If you have candidates, names for whom you would like to send out there, give us some, put it on a paper and give it to me. But more seriously, we've had some amazing opportunities to work with very different, strange concepts. Some time ago, I proposed that we put a mission that would include a lander for one of the lakes or close to the equator and a balloon in Titan's atmosphere that would go around the equator pushed just by the winds and would study the surface of the satellite and then graciously land on it sometime afterwards and make measurements, an orbiter to go around Titan. Because so far, except for the JUICE mission, which will arrive in 2030, there has never been an orbiter around a satellite. This would be a first. The orbiters are always going into the systems. There have been proposals for airplanes because of the dense atmosphere of Titan. It's a very, very favorable milieu to drop airplanes or to put aerostats or balloons. You don't need to do much. The air is there and it's dense enough that it can hold all of these things. And of course, having a lander would be very nice. This is the description of the mission that we had put together some time ago to try and look at the satellite with different kinds of perspectives. So it wasn't selected at the time. I'm hoping that by 2040, maybe, we'll get back to the icy moons around Saturn with at least some of these components, either with an orbiter or with an aerostat in the atmosphere or with a lander on the surface. But it would be nice to go back at some time, essentially because the Saturnian system is amazing. It has all of these moons, but Titan, the analogies with the Earth are very, very important. It's a potential habitat if you have the undersurface, water, ocean, you have the energy sources, the complex organic chemistry. Same for Enceladus. It's very important to go and study these bodies together also because beyond the habitability aspects, they teach us on some of the most important aspects of the Earth, the climate, the organic chemistry, and the emergence of life. I think these are very important elements that we need to take into consideration. We have these 2 moons here that are important and can teach us a lot of things. And all of this, of course, has bearings to the exoplanets, the bodies we find in other planetary systems, on which not only you can have planets like the ones we have discussed today, but also moons around planets that are there and could have the same properties as the Saturnian and the Cronian moons. So the water worlds are these bodies here, this huge category of objects in our universe that have not been studied so far. We have studied smaller silicate planets like Mercury or Earth-like. We've studied giant planets, but we have not so far have gotten enough information on the water worlds, these bodies with a lot of water inside that represent quite a huge amount of bodies in our universe. So this is what we're hoping to do with JUICE. JUICE is sitting here in this range of exploration of our solar system, going from the discoveries of the moons, the exploration of the deep habitats on the Earth, going then with the Galileo and the Cassini missions, the discovery of exoplanets, all the way to possible future landings. We really have a good opportunity with JUICE and the Europa mission to go and study these possible habitats. Let's not forget, some people have made the comment, okay, how about a different kind of life? And what, we need here may be different for some other forms of life that would actually land here and go ammonia, ammonia, instead of water. So this is important to bear in mind. If you want to learn a little bit more about an astrophysicist's point of view of life beyond Earth, we've put a book together with my colleague Therese Ancrenaz some time ago. And all I can say now is thank you for your attention, and rendezvous, several rendezvous, you can see them here at different dates in the future. Thank you.